We have now learned that the discrepancy between the theoretical strength of a material and the real strength of materials is very large. It's actually a factor of 50 at the most. And of course it's very important now to understand why we have that large discrepancy. It's important because if you want to know how to control the strength of materials, and also important for the understanding of the plastic deformation of materials. We will now start looking at the crystal structure. Here we see a crystalline structure. Most metals and ceramics, and also some polymers, usually occur in crystalline form. This is one of these typical crystal forms, actually one of the most common you see here. It's a so-called body-centered cubic structure. We can see that there is one atom in the center, and there are atoms in the corners of the cube. It can be depicted in this way, or in this way, and many other ways also. This is the structure of, for instance, ordinary steel at room temperature. But it's typical for a crystalline structure that this type of unit cell, as we can see here in the center or to the left, can actually show how all atoms are organized in the whole crystal. If you go to the picture to the right, you see here how the unit cell is shown in the corner here, but that unit cell actually can translate in all directions here. And the atoms are at the same positions all the way through the whole crystal. To understand the deformation of a crystal, we can assume that we put on a force here on this crystal, a shear force, a force in that direction, and a force in that direction, and then we will see how the crystal deforms. And then we come back to the picture we discussed before. We looked at the shear force that is pushing on the crystal in two directions, and we assumed in that case that all crystal bonds in one plane was broken at once. But we found that we got an unrealistic value of the material strength. So how does it work in reality? Let's go to the next picture. Until now we have assumed that we have crystals that are perfect, that is, crystal that has no defects. But in real life the crystals will have defects. And if you look at this picture, we see one of the typical defects in crystals. We can see it as an extra plane of atoms has been moved into the crystal like this. This is called a dislocation. Specifically, this type of dislocation is called an edge dislocation, as we have an edge here. And the dislocation is actually this area around this point. And as this is a cut through the crystal, the dislocation is a line defect going into the paper here. And we look now, how does it work when we put a force on dislocation, an edge dislocation? We have a force here, we're pushing on the top part here, and here we see the bonds. Well, earlier we discussed about all the bonds was broken, but now when we have a dislocation, only one bond needs to be broken at a time. We push here, and this bond will go over from this position to that position. So in the next situation we have a bond here, and the extra half plane has moved one step. In the next step, this bond is going to over to that bond. Then we have this situation where the blue bond is here. And we see that we have obtained a deformation of the crystal, one step to the right. Now there is a lot of different types of dislocations in crystals. It's easiest to look at the edge dislocation. There are also a lot of point defects in the material. All are contributing to the deformation mechanism of the material. But it's very important here to realize that due to the dislocation, due to the defects, only a few number of atom bonds need to be broken at the same time. And here we get an effect that this part of the crystal is going to deform relative to this part of the crystal only by a few bonds losing at a time. We will have a slip of dislocations in this plane. The slip planes are the most densely packed planes in the crystal, because there the distance for one dislocation to move one step is the shortest. Assume here that we have a plane that the crystals are very close to each other. The steps for the dislocation of this bond moved from here to here will be much shorter. unless you have a very large distance between the crystals. Also now, we will know that many dislocations are going to slip along one plane. So it's not only one that's coming here. So at the end, there's a huge number of dislocations have been slipping along the same plane. We can now look at the crystal structure, how the different planes can look. We now go back to this picture and see where do we have closely packed planes. Well, we can see that in this space diagonal of the unit cell, there is a relatively closely packed plane. And if you look in the total crystal here, we see that there is layers of these directions here. So this will be a slip plane in the BCC structure, the body-centered cubic structure. We can also realize there are a number of these types of planes in different directions. And of course it depends in what direction the forces are coming here, what planes will be the most active in the slip. But what is going to happen is there's a number of crystal planes that will be activated in the crystal when it deforms.